we're going to talk about the interesting rotational motion of rigid bodies. This football you see here is known as an axisymmetric prolate rigid body. Axisymmetric just simply means that it has an axis of symmetry. If you look at it down the nose here, the cross-section is a circle. It also means that it has only two moments of inertia, one around this axis, and then the other two axes have the same moment of inertia. It's a prolate body. Football is a prolate body, which means that the moment of inertia around this longitudinal axis is the smaller of the inertias. Now what I'm going to do is spin this football close to its longitudinal axis, but not perfect. This red line here, this red arrow you see, is actually the omega vector, the angular velocity vector that we'll talk more about. But if I begin the football spinning, once again, it's not a perfect spin on purpose here. What you notice is that the ball is spinning and it's also wobbling. And you see the omega vector is sweeping out a cone in space. So how can we understand this interesting motion? It'll help if we define some terms first. Here's our prolate body. There's an oblate body we'll talk about later. But I want to define these terms up here. Phi dot can be thought of as the precession rate. You might think of it as the wobble that you see. And psi dot can be thought of as the relative spin. It's not the spin of the body around its own axis, omega. It's something different. It can be shown mathematically that these two rates are actually related to each other and the moments of inertia. In the case of a prolate body, these two terms, phi dot and psi dot, are in the same direction, but they're actually opposite if Iz is bigger than Ia. They're in opposite directions. Also, notice that omega can be written in terms of these two different inertial rates. You might think of them as that. But a really useful way to think about this motion is this geometric interpretation of space cones and body fixed cones. Here's our prolate body here. It's got some omega vector. It's not spinning perfectly around its z-axis. It's wobbling. There's no external moment acting on this body, so h, the angular momentum vector, is fixed in space. So the cone that the omega vector sweeps out is also fixed in space. Now there's another cone that's fixed to the body that the omega vector will sweep out as the body rotates. And you can think of this motion as the body cone rotating around the space cone without slipping. And this omega vector has to be on the intersection of those two cones, because omega is associated with each of these. If we go back to the spinning football here, once again, you can see the omega vector sweeping out this cone in the inertial space. It's also moving relative to the body as well, but that's more difficult to see. So if we put ourselves in the body frame, we fix ourselves in the football's frame. You notice the laces over here on the left, they stay put relative to you. Notice what we see. The omega vector in this body fixed frame is moving clockwise in our perspective here. Same as the ground behind it. Okay, they're moving in the same direction. Okay, let's go look at an oblate body and see the motion for that. Now let's change the rigid body to a frisbee. This is what's known as an oblate body. So an oblate body means that the moment of inertia around the symmetry axis, the spin axis in this case, you might think of it that way, is the highest moment of inertia. It's higher than the other two moments of inertia. If we start to spin the Frisbee, once again, I'm spinning it in a way that it's not a perfect spin, so you can see the wobble. You see, if you remember the spin of the football before, it looked like everything was going counterclockwise. You see I've got a little cutout in the Frisbee here. You can see it's sort of spinning, if you look down on it, kind of counterclockwise. This omega vector is also spinning counterclockwise. The little axis indicator I've got here is all counterclockwise, doing the same exact thing that we saw with the football. You see here for an oblate body, the cones are a little bit different. Okay, in this case, in the case of an oblate body, the body cone is this big cone. That's fixed to the body. The space cone is smaller. And so the space cone is actually on the inside now instead of being on the outside. So when the body cone rotates around, the path of the omega on the space cone is the same direction it was before. Okay, but the path of omega on the body cone is actually in the opposite direction now. If we change our perspective again and lock ourselves into the body fixed frame, you see we're moving around with the Frisbee looking right down that z-axis. You notice in this case, the omega vector sweeping out the cone in this frame is actually moving the opposite direction to what you see the world spinning behind it. So you notice it's going the opposite sense as what we saw in the prolate case. This is what's known as retrograde precession. I think that name is a little bit of a misnomer because what's retrograde is not the precession. It's really the inertial, or sometimes called relative spin, psi dot. And that's what you're seeing in this simulation right now. The last type of body we're going to talk about is what's called a general rigid body. And that's a body that has three different moments of inertia. So there's a major axis of inertia, an intermediate axis of inertia, and a minor axis of inertia. Now, the vehicle you see in this simulation is a scaled down F104, and it has three different moments of inertia. It's got its minimum moment of inertia around its longitudinal axis. We can change the perspective here so you can see it a little bit better. So there'd be one moment of inertia around this axis. That's going to be the minor axis. The intermediate axis, so to speak, is going to be along this direction, the pitch degree of freedom we call in aviation. And then there's the major axis of inertia is going to be about the z-axis, this direction. Okay, so if I spin this F104 around the longitudinal axis, but once again, not perfectly. I have a little bit of omega in the other direction too, so there's a bit of a wobble. And so you can see here that the vehicle is spinning around in roll, but you also have this motion of the omega vector, which we talked about before with the axisymmetric bodies, which represented the vector going around the so-called space cone. If we look at that in the body frame, what you'll notice is that the world behind the airplane, you see in this case, is spinning clockwise, and the omega vector in the body fixed frame is also rotating the same direction. Now I'm going to spin this F104 around its major axis. Once again, not perfectly. I want it to wobble so you can see that motion. So you can see the airplane generally rotating around the major axis, which we'd call the z-axis, and there's also this wobble of the omega vector in the inertial space. I can change my perspective to lock myself into the body fixed frame. What you'll notice here is the sky behind the airplane is actually rotating clockwise, but now notice this omega vector is going counter to that, counterclockwise. Kind of similar to what we saw with the oblate body. But you notice in this case, in the case of the general body, the motion of the omega vector is not a circle. It's more elliptical. Now let's spin this body about the intermediate axis. And this is the axis that is really interesting. You notice here that the omega vector is out the starboard wing, and so this airplane should begin pitching up. I've put it in almost a perfect state of spin in this case, unlike the other two. I'm not trying to incite any kind of wobble at all. Notice the airplane starts pitching up and then it just completely changes direction. It's really interesting phenomena. It's going one direction, then it flips over and goes the other direction. Once again, this started out in essentially a pure state of spin around the intermediate axis. Changing perspective to lock it into the body frame, you see something interesting here. The omega vector is pointing at you. Now it's pointing away. It's pointing at you and away. Look at the world behind the airplane. There's pitching up. Now the airplane's pitching down. Now it's pitching up. Now it's pitching down. One way to interpret this motion and what's going on is to look at what are called polhodes. This ellipsoid right here is what's called the H, or angular momentum ellipsoid. Basically what this is if you imagine this is the minor axis of the airplane, so this would be pointing straight up. This is the intermediate axis, and this is the major axis. These paths that are called polhodes on the H ellipsoid are where the omega vector, the point, the tip of the vector, touches this ellipsoid and traces out a path. So remember when we saw, when we spun around the minor axis and it was wobbling a little bit, what you were seeing is the vehicle undergoing this type of motion. It's a stable motion. It would just continue doing that forever. That omega vector sweeping out this ellipse, you saw as the wobble, so to speak. Same kind of thing with the major axis. When it was spinning, you see this omega vector sweep out a path like this, and it's a stable path, and it just continue on indefinitely. But what's interesting is the intermediate axis. These paths on intermediate axis, if you're coming this direction, you'll notice the paths go into this point, whereas you also, from that same exact point, you have potential paths that go in the other direction. This is known as a saddle point. So bottom line is that intermediate axis spin is inherently unstable because of this saddle point right here. And that's what you were seeing with that omega vector flipping, going one direction, going around, and then picking up and going the other direction. So that's why intermediate axis spin is unstable, and it's such an interesting phenomenon.